All right, so today we're going to learn about implicit differentiation. It sounds really good. Go ahead, say it. I'll pause. Didn't that feel good? Implicit differentiation. So the problem with this thing is this is a circle, right? It's a circle, you know this. It's a circle centered at 0, 0 with radius 4. So we're going to find dy dx. So let's go ahead and try that. You can take the derivative of everything if you wanted to. So that's what we're going to do right now. We're going to take the derivative of the left like we've been doing, and we're going to take the derivative of the right like we've been doing. We can split that up. This is a sum. So we're going to take the derivative of x squared plus the derivative with respect to x of y squared, and the derivative of any constant, doesn't matter what the constant is going to be 0. So we've done this before. D dx is going to be 2x. We haven't done this before. This is kind of a new thing for you. D dx of y squared is 2y dy dx. So here's what we did. We took the derivative of y squared and got 2y. But we have to do the chain rule, right? The chain rule says take the derivative of the thing on the inside as well. So that's where we get this dy dx. If you think about it, we actually did the chain rule up here as well, right? So if I take the derivative of this thing, it's 2x times the derivative of the inside, which is just going to be the derivative of x, and the derivative of x is 1. Or, thank you, dx dx, right? So the really, really important thing from this lesson here is when you take the derivative of y with respect to x, that's what we're calling it here, dx, we're taking the derivative of this thing with respect to x, we need to do the chain rule. Drop the 2 down in front, y to the first, that's where I get this, but then I have to take the derivative of the inside function as well, which is y. That's where the dy dx comes from. So let's backtrack a little bit here. Oh, that's why I couldn't see it. It was in the way. I wonder if I can move this. Nope. I just have to pause, wait for it to go away. Okay, so we're on this step right here. So I went ahead and I found the derivative of this, that's that. I found the derivative of the y squared, that's where I get the 2y dy dx. And now what I'm going to do is I'm going to get the 2x over on the other side, divide both sides by 2y, simplify, and I get dy over dx, which is literally the derivative of y with respect to x equals negative x over y. So that's where we've been. Dy over dx equals negative x over y. This expression, this is the expression for the derivative, which involves x and y. So before it was interesting. The y, we didn't care about y when we were finding the slope of the tangent line, right? The y didn't come into play. It didn't affect the tangent line at all. It was just the input that affected the tangent line. Here, because we're doing implicit differentiation, we have an x and a y. So the x and the y are both going to affect the tangent line, not just the x anymore, but the x and the y. This is really cool. So if you think about it, this is my circle right here, right? So this is my original equation is this blue equation centered at 0, 0 with a radius of 4, right? So the slope of this line right here, the slope of this gray line is going to be rise over run. So if the point's at a comma b, the slope is going to be b over a. And the slope of the green line that we just found out is going to be opposite of x over y, and x is a, y is b, so it's opposite a over b. So if you think about it, they're opposite reciprocals of each other. And it just makes sense. They're opposite reciprocals of each other because the tangent line of a circle will always be perpendicular to a radius. I don't know if you remember that from geometry. Let's go through an example real quick. So for this curve, we're going to implicitly differentiate this thing in terms of x. So we got this curve right here. We got x cubed plus y squared minus 2xy equals 2. Normally you just try to solve for y and then take the derivative. But here it's going to be a little bit tougher. Notice this isn't even a function. This is cool because we're going to have derivatives here on this side. We're going to have derivatives here on this side. just because it's not a function doesn't mean it's not differentiable, right? We can still find the derivative of this thing even though it's not a function. So let's go ahead and try this. Let's take the derivative of the left and the derivative of the right. Let's split it up. So when I look at this, I see a sum and a difference of the two, right? So we're going to take the derivative of x cubed plus the derivative of y squared minus the derivative of 2 times xy. So that's where I get the 3x squared. Drop this down, do the chain rule, and then here we got the multiplication rule, derivative of the first times second plus the derivative of the second times the first equals the derivative of any constant. It's going to be 0. Now what we're going to do, I'll have to pause for a second, is we're going to get everything that has a dy dx on one side of the equation, and we're going to get everything that doesn't have a dy dx over there on the other side of the equation. So we're going to have to manipulate the equation a little bit. And from there we can factor out, because on the left side of the equation we have a dy dx in both terms, so we can undistribute, or we can factor out that dy dx. And then finally we can divide by the thing that is being multiplied by dy dx. So we can divide both sides by 2y, the quantity 2y minus 2x. I'm sure Mr. Pardon is not going to like that I just called the quantity 2y minus 2x a thing. But hey, you're going to have to deal with it. Here's some new notation for you, right? So what we're doing now, because we found the equation of the tangent line, we found the equation of the tangent, but we did not actually evaluate it at -1, 1. So notice that this is not in like a function notation. dy dx, there's no parentheses to tell you what the input is, because there's actually two inputs. There's the input that we need to plug into x, and then there's the input that we need to plug in for y, because both x and y affect the derivative of this. So the way we read this is dy dx evaluated at -1, 1. So whenever you're going to evaluate or find the slope of the tangent line at a certain point, this is how you're going to write it from now on. And we're just going to substitute in, let me move my picture here. We're just going to substitute in x and y for x and y. And then finally that gives us -1/4. Boom. Kind of a longer video. Try to keep it under 8. Let's see if I can do it. Nope, it's not going to happen. There's the notation that we talked about. The last thing that I have for you is the difference between dx and dy dx. One is a verb and one is a noun. So remember, a verb is an action and a noun is a thing. So if you ever see this notation, d dx, that means, hey, I'm about to take the derivative of this thing. I did it again. I'm about to take the derivative of the quantity x squared plus y squared. Versus if I see this thing that says that I already took the derivative, right? I took the derivative of dy dx, and it's right there. So let me let that go away real quick. Yeah, so the second one is the product of the derivative of y with respect to x with the quantity. There it is. See, I told you who would write that in there. The quantity x squared plus y squared. Okay, so that's all I got for you. Really good stuff. We'll see you guys soon. Peace.